Hello, I'm going to put this or make this screencast on homeostasis and regulation and this negative feedback concept here. Uh, so we're going to be down here explaining how negative feedback mechanisms help to maintain this concept of homeostasis. Now, so homeostasis, it can be synonymous with regulation. Right? So regulating regulating life processes. Nothing happens constantly, or at a steady rate. So this concept of regulation and negative feedback is a mechanism of maintaining homeostasis. So a mechanism, again, is how something is going to happen. How something happens. So oftentimes they'll ask you to describe or explain a mechanism, and they want you to explain like how something is happening there. So if we look at our images over here, we have this hypothetical series of reactions where A is converted into B, is converted into C, is converted into D. And we are assuming that these reactions here are all mediated by an enzyme at each step in the process. So this would be enzyme sub A, for instance, right? So enzyme sub A converts A into B, and then this would be enzyme sub B, which is going to convert B into C, so on and so forth. So if this series of reactions is happening, then our concentration of D here is going to be ever increasing because this reaction is just going to keep happening and happening and happening. Now, if you have this reaction going, you are using resources and using energy, presumably, to get this job done. Now, it's presumed that you probably don't want to be wasting resources, wasting energy here, making a whole bunch of this item D when you don't need it. So a way to regulate that, a way to control, maintain levels of resources, energy, and even the concentration of this D is to have D, what we say, feed back. Right? So D feeds back and will then negatively, with this negative feedback, I'll talk about that, the negative part of this in a second, but this feedback is some sort of signal then to stop making more of this item D here. So in this case, we're going to have D feeding back and acting as an inhibitor, allosterically or competitively to this enzyme sub A, right, with this substrate A. So if we can shut this enzyme down, if we can shut this process down right here, then notice we don't make B, we don't make C, we don't make any of D. Then the assumption is that either D is going to stay high or D will be used. And so if D stays high, then this whole reaction remains shut off. But if D gets used, then the concentration of D is going to come down. So over here we see that the concentration of D has been diminished here. So we have no D, indicated by this being less dark here. And this is also a negative feedback. So this lack of D also feeds back. This lack of this substance here is going to feed back, and now in some way is going to signal enzyme sub A to pick back up again and be converting A into B, and then of course then B's levels go up, so then there's substrate for enzyme sub B to convert that into C, and then so on and so forth. And then as this reaction, these sets of reactions go on, the concentration of D is going to come back up again. Right? So then concentration of D goes back up. Right? And then we're back to this situation again where the levels of D are above a certain point, and they're going to then feed back here and inhibit A. So graphically, you can have this, these three images sort of in your mind, but also graphically, what is helpful to see is that over time, the levels, right, or whatever you have here, whatever variable is here, is not going to be, so in this case, this would be, a concentration of D, say. Right? Well, it's not going to be just a static straight line. You're going to have this constant increase and then decrease and an increase and then decrease and an increase and a decrease and an increase and a decrease of this D, where you have this upper limit and you have this lower limit. There's an upper limit there, right? And then there's a lower limit here, and this concentration of D exists within a range. Exists within a range. Right? So it's not the static. Now the average of D, of course, is going to be somewhere straight down here, but this hardly ever really exists. It's really this sine wave, right, of up and down, and you exist within this limit. Now, as the levels of D are approaching this upper limit, there is a signal then, right, that is sent here to this enzyme sub A to then begin to do something to make those levels of D come back down. So what we're saying here is that, can you go above this limit? Yeah, you can go above the limit, but if you stay above that limit for too long, this is what's going to happen to you, right? You're going to not be surviving very much longer. And also this, if you stay below that limit for too long a period of time, that can also lead to death. So this is where this negative aspect of negative feedback comes from. The negative part of this, and this is kind of the way I think about it because it helped me. This was confusing to me because I was thinking like, oh, negative feedback. How is this negative feedback when it's positively stimulating? It's causing this reaction to go up here. And then I finally dawned on me that, oh, wait, once I drew the graph like this down here, that the negative part is meaning something's going to happen to stay away from the upper or lower limit, right? Negative, go away from that upper limit, go away from that lower limit, right? Or if you go beyond that lower limit, don't stay down there too long because you're going to die. If you go up above that upper limit for too long, you're going to die as well. So hopefully that helps. Getting this image right here, this graphical image, into your mind, I think will go a long way to understanding this homeostasis and this maintenance of a balance, right? That life exists within a range, right? So we see these curves, this sine curve, in lots of different places, and at lots of different levels of biological organization. For example, negative feedback mechanisms maintain homeostasis at the ecosystem level. So here we're looking at hare population size, right? And so hares being a prey item, and we're looking at then time here. And what we see is that we're looking at the prey population, but then we're also looking at the lynx population size as well. And these lynx are predators, right? Now, the color scheme here on yours is it's black and white. On your papers, it's black and white, so you may want to add some color there to it. But the lynx populations are in red, right? So let's change to red here. So the lynx are the predator populations. And what we notice is that I went back to the wrong slide. What we notice is the prey populations here are, even though it's a little jagged, but we still see this oscillating up and down, where the average of the prey population, right, is at an upper limit, is at a lower limit. So what is keeping that prey population, quote, in check, right? What keeps it in check, of course, are the predator populations. Now you'll notice that the predator population is also oscillating up and down, up and down. So you have this rough sine wave here. But the predator population is lagging behind that prey population, because then the thinking goes, okay, if there's a lot of prey out there, then that can support more predators. So more predators, more energy in, more reproduction. You can make more of those predators. But then more of those lynx are in the population. They need to feed. So then the snowshoe hare population is going to then come back down as more predators are out there eating them. Then there's less food out there to support those predators, and so then the prey populations are going to be able to rebound, right, after that. And so you have this oscillation back and forth, right, keeping the population sizes in check, in homeostasis, in balance. The population sizes are regulated. We can look at homeostasis at the organism level as well, the organism organ levels. Right? Many of you have heard of diabetes, which is associated with blood glucose levels. But in normal situations, not diabetic situations, in normal situations, the blood glucose levels are regulated. So after a meal, that's a stimulus, so this is rising blood glucose levels, right? This is the stimulus, will then signal beta cells of the pancreas to release insulin into the blood. That insulin then is a signal to body cells to take up more glucose and for liver cells to store that as glycogen. So in response, blood glucose levels are then going to come back down to a set point, right? And the stimulus for insulin then diminishes. So the beta cells stop producing insulin here. Beta cells stop producing insulin. So this hormone insulin secreted by the beta cells helps to bring the blood glucose levels back down. Consequently, if you haven't eaten a meal in a while, this is also a stimulus. Right? So blood glucose levels are going down. Now different cells of the pancreas, the alpha cells, are going to secrete then glucagon, which is a different hormone. Glucagon has liver cells as its target cells. Right? So the alpha cells secrete glucagon. Glucagon then signals the liver to break down glycogen and release glucose into the bloodstream. Right? So this glucagon signaling right here brings the blood glucose levels back up, because glucose is being released into the blood, and your blood glucose is going to return to that set point. Right? So even though it's not shown on here, you could be thinking that this is BGL, blood glucose levels, and then over time, and you see that as your blood glucose levels go up, insulin then helps to bring those blood glucose levels back down, and as the blood glucose levels go back down, glucagon helps to bring those blood glucose levels back up. And there is a set point here where there's an upper limit and a lower limit to this. And again, if you can go above, but if you stay up there for too long, that's going to lead to problems. And if you stay down below that too long, that's going to lead to problems. So this homeostasis, right, boom, here, right, sine wave, maintaining a dynamic equilibrium there. And then finally, negative feedback mechanisms maintain homeostasis at the molecular level. So this happens in enzymatic rates as well. For example, if we take this initial substrate threonine right here, we're trying to convert that into isoleucine. Right? So this is an amino acid. This is an essential amino acid that our bodies need, that cells need, and this is a non-essential one because our cells can make this one, and we make it via a whole series of reactions here. So again, here we see this concept. Here's enzyme number 1, threonine deaminase. That's going to make this intermediate A here, which is a product. Then this product becomes a substrate for enzyme 2, which gets us this product 2, which becomes substrate 3. Enzyme 3 converts substrate 3 into product 3, and so on and so forth, until you end up getting this isoleucine down here as the final product. Well, now this concentration of isoleucine is going to constantly be going up here, and that is going to act as a signal. Right? So this is, here we go, feedback inhibition. This is going to signal this enzyme number 1 up here, threonine deaminase, to slow down this whole process here. And it turns out that this this isoleucine down here binds to an allosteric site on this enzyme, changing the active site, right, thereby decreasing induced fit between threonine and threonine deaminase, and this whole process then slows down. The assumption, of course, would be that isoleucine would be being used, and therefore the concentrations of isoleucine would go down and would not bump into this threonine deaminase as frequently, and your levels of isoleucine would come back down, and then you'd have this reaction process going again there. So just a quick question about this to end on for you just to consider. What would the, so if this is isoleucine concentrations, right, and time, what would the graph look like if isoleucine A was not used up, and what would it look like, what would the graph look like if isoleucine was used? So take a second up here on this set of axes, graph those two, and we can talk about that in class. Okay, thanks. Hope that's helpful. If there's questions, bring them to class.